Okay, let's start. Um, it's good to be back. I'm really waiting for next week to see you all face to face. And I really want you to participate in class. It's hard enough to talk in front of an empty class, so please be as responsive as you can. Okay? Thanks. Okay, so, oh, by the way, I checked your homework and you did a great job. And I just wanted to say that you can write much more concisely. I'll appreciate it. I'll give an example during the talk, and we'll see. Okay, so today's topic is expander codes. Can you see it on the board? I'll try to. How about now? Should I use another one? Better? Okay. Expander codes. So before I talk about these codes, I need some definitions, and maybe you saw it earlier on the course, and you didn't. I'm not sure. So let's talk first about bipartite expanders. So what's a bipartite expander? Basically the same as an expander, but instead of being a sparse approximation of the complete graph, it's a sparse approximation of the complete bipartite graph. Okay, so what do we know about generally when we have an expander G, which is an omega expander, so we have like eigenvalues 1, which is omega 1, omega 2, omega n. We have omega equals maximum of omega 2 plus value of omega n. Right, this seems familiar. So in a bipartite graph, the spectrum is always symmetric. So the last eigenvalue must be -1. And definition of the spectral expansion is just omega equals omega. Okay, because this one is trivially 1. Okay, so how can we generate such expanders? So let's say we have one partite expander G with random walk matrix W. So we can define the adjacency matrix. Looks like this. And this will be a bipartite expander. Okay, why? Because if Wx equals omega x, then B times xx equals Wx. Okay, and B times x minus x equals okay, so if we had an eigenvector of W with an eigenvalue omega, we found two eigenvectors, xx and x minus x, that are eigenvectors of the new bipartite graph, and it has eigenvalues omega and minus omega. So this is a contraction.
But in order to say that it's the omega, we need to say that we don't have anything that is larger.
So this is a characterization of all the eigenvectors of the new bipartite graph, right? Because there are
Right, okay.
there are n eigenvectors to W. So these are two n eigenvectors to B, and these are all the eigenvalues and eigenvectors. Okay, so we already saw in the course how to construct expander graphs, and now you also know how to construct bipartite expander graphs. Yeah, okay, let's move on, and let's remember some things about linear codes. So what's a linear code? So we say C N A of the alphabet soup code. Now, uh, simply if its code words form a linear subspace. Say is a linear subspace of Q to the n. During this talk, I'll only need binary codes, so let's just stick with that. Okay, and what do we know about linear codes? Three important facts. How can I characterize the distance of the code in a linear code? Okay, what does it mean?
Minimal weight.
Yes, so the distance of the code C is by definition the minimum of all x and y. X, y in C. Distance between x and y. But in a linear code, this is just the same as minimum of W. You take code word, a non-zero code word, and just check for its weight. Right? You saw it in the course. Maybe I'll just explain why. So if C is a linear code, so we have distance between x and y. It's the same as the distance between so let's just shift these two words by x. X minus x and y minus x. This is 0 and this is y minus. So instead of iterating over all pairs, I just iterate over 0 and all possible non-zero code words because I only iterate over x not equal y. Okay, so that was the first fact. The second fact is, oh yeah. So every linear code has a parity check matrix. And so there is each dimensions okay, such that h x equals 0 if and only if x is a code word. Right, it's just the, I think you should choose a basis for the complement subspace of the code.
Not the complement, the orthogonal.
The orthogonal, yes. Okay, so we have a matrix H, and there is matrix, usually they call it G, called the generating matrix, such that C is just the image of G. Okay, so I'll need these facts about linear codes. Okay, any questions so far? Okay, so let's move on to talk about the construction of the expander codes. So what we have in mind, is a bipartite expander. Irregular and an omega expander, and has two sets of vertices, L and R. Each of them is size n. So I have 2n vertices.
Are we constructing a better bipartite expander than the previous construction that you showed?
No, now okay, I should have said that. Now we want to construct an error correcting code, a linear error correcting code based on expander graphs. Okay, that's our goal today, to construct this code and analyze it and describe an decoding algorithm for it. So we start with a bipartite expander graph. And I now need to describe the code. Oh, each vertex labels. Okay, so vertex 3 chooses arbitrary order. It doesn't. Okay. Can you see the numbers on the board? Okay. And okay, now I need to describe the code. So it's going to be a linear code, and it's going to be over MD variables. Going to have a rate and the distance that we'll figure out later, and it's going to be binary. Okay, so this is a hint. Where should I put my bits on the graph?
On the edges.
On the edges, right? So each code word is interpreted as an assignment of zeros and ones to the edges. Okay. And so the words in the code are assignments of 0 and 1 to the edges. Now, each vertex has a constraint. Each vertex must see a code word. I've got to say something important. Let's go one step back. I need, for this construction, I need a small code. Let's call it C0. This is a linear code. T variables. C0 and this. So it was important. Okay, so let's start from the beginning. I have this code. It's easy to construct because I think of D as a constant, so I can just find such a code. And now I'll use this code in order to construct an expander code of any size I want. And okay, so I have this code. and I have this expander, and I find I think of the words in the new code as assignment to the edges. And my constraint is that each vertex, okay, so V, maybe, so from the perspective of V, it sees the vector 1, 1, 0, 1, right? And I want it to be C0. Let's set it for every V. Okay, is it clear?
Itay, can I ask a question?
Yeah, sure.
So in the view of the vertex V, it does matter how does it label the edges, right?
Yes, it's true.
So you need like something apart from the adjacency matrix of the graph, or we
Yeah,
don't.
so I assume the graph comes with a labeling, an arbitrary labeling. I don't mind
Okay,
how each vertex labels its label.
thank you.
Okay. Okay, so now the first question you should ask is, are there any words here at all? Because there are many constraints. How can I guarantee that they can all work together? Right? Because yeah, is the question clear?
You
And,
mean non-zero words?
What?
You mean non-zero words?
Yes, except for 0, which is clearly a valid word. Okay, and the reason are words in this code is that these are linear constraints. Okay, so WB in C, if and only if a linear constraint happens. Okay, so how many constraints are there in the code in this construction? So there are two end vertices. Each one of them has a linear constraint of the form hx equals 0, but this is actually not a single linear constraint, but n minus k linear constraint, where n is d and k is k0. Right? So this is the number of linear constraints. And what is the dimension of the whole space?
2 to the dn.
The size of the space is 2 to the dn, and the dimension is dn.
Okay.
Okay. And this leaves us with, let's take the d out. Okay, well, rho 0 is just k0 divided by d, the relative rate of the original code. Okay, I just took the d out from these parentheses and moved the terms. Okay. Okay. And okay, so what can we see now? So if rho 0 is larger than 1/2, then this term is larger than 0, and I have the dimension is positive. Okay, and I have code words in my code, and I even computed the rate of the new code. Okay.
It's not if and only if, right? They might be dependent, some of them.
Yeah, exactly. So it should be the dimension of C is at least this amount, and perhaps I can choose the labeling so that it will be even better, but I don't want to go there. Okay, let's see. Okay, so what we need to do is to compute the distance of the code, of the new code, and to show a decoding algorithm. Let's start with the distance. So as we said before, this is didn't say why this is a linear code, but it should be clear. Okay, if W1 C and W2 C, so why would the addition be in C? Because the constraints are linear, right? I should have said it before. So since C is a linear code, it suffices to analyze its lightest code word in order to determine its distance. So let's do it. Okay, so let's take a non-zero code word, and it has some zeros, many zeros, and some ones. And I want to claim that there must be many ones, right? To say that the distance is large, I need to claim that there are many ones. Okay. So let's denote. So we have a word W, which is the lightest, and let's denote F, the set of edges that for which W assigns the value 1. Okay. And I want to claim that F is large. Okay, so what's the distance of the code in terms of F? Oh yeah, just the size of F. I meant there's always the normalization.
Relative distance.
So small delta, the relative rate is F over ND, right? Through the analysis, we'll normalize different things with different normalization. If you take a subset of vertices from the left and you want to take its normalized size, you need to divide by n. F you need to divide by nd. Some things you need to divide by d to normalize. So it's important to keep track of the correct normalization for each I don't know, for each creature. Okay, so what can we say about take a minute to think
What can we say about what?
about the size of F. How can we bound? What we want to show now is that the size of F must be large. How can we claim something like that?
We can start hop around.
Let us first state the expander mixing lemma for bipartite expanders. Okay, this is very similar to what you proved in the homework, and I want to talk about it for a minute. So, Okay, so this is the expander mixing lemma, right? So it looks familiar. And I think the overlay. And the way to prove it is really simple. And in the homework, many of you wrote pages and pages of proofs. The easiest way is just to take just to look at one transpose S. The expander G times 1C, right? All of you did it in the homework. And then you can just write W as J plus E when J is just the all ones matrix normalized in the correct manner, and E is a matrix of norm omega. And E is perpendicular to the all ones vector. And then you decompose 1T and 1S to 1T equals 1T parallel 1T. Yeah. This is the um, 1T parallel is just the projection to the all one vector. And then you just plug it in and everything solves itself. And my point is that if your answer in the homework is too long, there's probably a shorter and cleaner answer. And I'll appreciate it if you will find it. It's both good for you for learning how to do the things in the correct and cleaner manner, and both for me for checking your homework. Okay, let's move on. So this is the standard mixing lemma for bipartite expander, where S is a subset of L and P is a subset of R. Right? Because of course you can take two sets in the same side and there will be no edges at all between them. Okay, and the proof goes just the same. You can just write, so you have the matrix WW, and you can just write it as JJ plus EE, and everything works just the same. Expand the mixing lemma for bipartite graph. Now, how can we compute the distance? So let us start with F. Why is that? Oh, I didn't find S. Sorry. So let us denote S, all vertices on the left that touch F. And T is the same for on the right. Okay. So now tell me why this must be true.
Because each one sees a non-zero little code word. So this little code word needs to be at least delta 0 ones, and they are disjoint from the other ones.
Yes. So when a vertex single edge that is labeled 1, right? Because it has to see a word from C0, and in every word in C0, there are at least delta 0 ones. Okay, again, because it's a linear code. Right? So each vertex in S sees at least delta 0 edges in F, and we have this relation. The same goes for and okay. Now let's use the expander mixing lemma in order to bound the size of it. So I'll need both of these bounds, so let me combine it as F rather than okay, it's just the average of these inequalities. And on the other side, is at most the number of edges between S, T, and this is at most using the expander mixing lemma, D over N times T times S plus omega. Okay, so now there are some ugly tricks, but let's do them once, and then in the next times, just say use the same ugly tricks for from before, and we'll skip. So we have this inequality, and let's just clean it a bit. Trust me, this is nothing more than normalizing things correctly. Okay, well, S equals side of S over N, and P equals the side of P over N. Okay, so this equation simply translates to this equation by multiplying by the correct normalizations. Okay, nothing interesting here, but how does this help us to bound the size of F? Okay, first of all, I want to claim that this term is at most omega. And the way to see it is that square root st is smaller or equal to s plus t over 2. And this is just the inequality of the geometric and arithmetic mean. Okay, so the right term is simply smaller or equal to omega. Okay. And you must ask yourselves, how is this going to get us a bound on F? Because there is no F in here, and now comes the trick. So we write 2st is smaller or equal than s squared plus t squared, which is again the inequality of the arithmetic and geometric means applied on the s squared and t squared instead of s and t. And now, so this is like s times s plus t times t, and I use this bound on this s and this t. So s plus t times each one of them I replace by f over delta 0. Organization. Okay, so I bound this element by, let's write it in a same as S less than or equal to F over delta 0 and 1. I plug it here and here, I get this. Okay. Great. So now I plug it back here, and I have F on the larger side, and let me just keep the math, and we get okay, let me just write the bottom line, because the interesting part we get kind of F. Let's just write it. We get delta larger or equal than delta naught squared over 2. Okay, but I think the important thing to take from this proof is that is the use of the expander mixing lemma. Okay, we wanted to claim that F must be large, and then we said, okay, we have vertices on the left and on the right that touch the edges in F, and why F must be large? Because these vertices must expand. This is why we need an expander. Okay, that's what we get. And now I want to assume that that the expander, good expander, which will give me this is my assumption about the expansion, and I'll get a lower bound on the distance. So it was a little messy. Okay, let's move on. So we saw that the rate of the code is 2 row 0 minus 1, and we saw that the distance of the code is delta naught squared over 2, and the only thing we have left is the decoding algorithm and 13 minutes. So not enough. Let's start. Any questions so far? Okay, so decoding algorithm. And so how is it going to work? We're going to first need a correcting algorithm for C0. So assume we have an algorithm that takes W0 in 0, 1 to the D, and if W0 is close to C0, then so it returns the code word that W0 is close to. Let's call it C0, and let us draw an example. So this is C0, and these are the code words. And my algorithm has a guarantee that if I get a word W0 near the code, near one of its code words, then the algorithm corrects it. Okay, returns this is a W0 and this is C0. And what happens if it gets a word that is not close to the code? We don't care, it just returns an arbitrary string and it won't matter to our analysis. Okay, so we have this code, this algorithm in hand, and we want to create such an algorithm for the expander code. So how are we going to do this? So it will be very simple. Simply go over the left side and correct each one. Okay, so get to a vertex V, and then you see a word, and you plug it in the algorithm, correct it, and write it instead of. Okay, so we might have send the word 1 1 1 1 0 1 to the algorithm. Can you see? And the algorithm may return, let's say, 1 0 0 1, and we'll just write it back. So just the algorithm is just correct the left side, and then correct the right side, and then correct the left side again, until you finish, until there's nothing left to correct. And your first answer and your first question should be.
Does it stop?
Yes, perfect. And the answer is yes, it stops. Given that you give me a word that is close enough to the code, it stops.
And without this assumption?
Without this assumption, I think I don't know to say anything, but if you want, you can just run for sufficiently many steps and then halt. So it won't hurt your runtime. Okay, so this is a bit, the proof is a bit tricky and it's very confusing, but let's do it quickly. So we have this algorithm. Okay, so we get in mind a word W that is close to the code. So I write it C plus E. Okay, and I know that E is light. I'll plug in the parameters in the end, but for now, just think of E as a light vector. And I want to start with a lemma that will help us to prove that the algorithm converges quickly and so on. And the lemma says that if omega is good enough, and again, I need to define. So define S1. So now I have a code word and I have some faulty edges, which I don't know where they are, but this is only for the analysis. It could be also 0 edges that are faulty, 1 edges, this doesn't work. Some faulty edges, which I don't know where they are. So let's denote them F faulty edges. And then denote S1 vertices on the left that touch F at least once on L that touch F. And define P delta 0/2 if vertices on R what? This is a hint.
That touches at least delta over 2 of them.
Wait. Okay. And okay, so we have some we have these guys, vertices on the right, that touch many faulty edges. Okay. What we're going to claim is that okay, we'll need an additional assumption that S is small enough. What we are going to claim is that T is much smaller than S. This T and this S. Okay? I omit the subscript. I see I'm going to need another 5 or 10 minutes after the class. I hope you are fine with it. Much smaller. Okay? 3/4, 3/4. Okay?
Little s is the many,
This is capital S. And
which is S1. S is S1.
yes,
What
yes,
is,
I omit the subscript. I omitted the subscript.
and little s is the size of big S over n.
Okay.
And later on we'll omit this assumption.
What?
And later on we'll omit this assumption about little s.
One?
Yeah, this one.
No, we won't. We will demand that we start with a word W that is close to the code, and we'll deduce that S can't be so large because W is close to the word, because E is light.
So we'll ask E to be that. Delta 0/9.
I think it's gonna be delta 0/18 or something.
Okay.
Well, I don't know. We'll see later. Okay, by the way, I should have said it before. You can see here what we're claiming is about not the distance of W from the code as the algorithm runs, because in a single step, a single correction of the left side, it can actually get further from the code. But we focus on the vertices that touch faulty edges, and these must shrink rapidly as the algorithm runs. Okay. Okay, but if you ask yourselves, correct that side, why would it cause the number of boosts to reduce? It's not necessarily the case. This is not what we are trying to say. Okay, we look at vertices that touch faulty edges, and we say that they disappear rapidly as the algorithm runs. Okay, so let's prove this. Is like this. And once again, we'll use the expander mixing lemma. So the point here is that we have T delta 0/2, the set that has many outgoing edges. And these edges must expand, and each vertex here must be in S1. Okay, so we have a small set that has many outgoing edges on an expander. So it must touch many distinct vertices. So S1 must be much larger than T. Okay, much larger is like multiplicative factor. So we'll use the expander mixing lemma. E S T. On the one hand, you use the V over N size of S size of T plus the omega, blah, blah, blah. And from the other side, how can we bound from below the number of edges? So it will be size of t times the right? Because the right side I have inside T I have vertices that see manifold edges, and each such edge is between S and T. So this is the bound, and now I'll skip the same tricks as before with the inequality of means and so on, and I'll tell you that this gives me T smaller than omega S over delta mu 2S minus omega, plugging in assumptions about the parameters, it gives us. Okay, but again, the main point of this proof is that we use the expander mixing lemma to bound the size of T with respect to the size of S. Okay, any questions? Okay, well, really, we don't have much left. So this was like a static argument about just like a natural fact about expander graphs. And now let's talk about our algorithm. Okay, so we'll have a correcting step. Now, okay, let me do this. So I have a correcting step, correcting left, and then I define F the new faulty edges, and I call S1 the vertices from the left that touch faulty edges, and then I run correcting on the right side, and then I look at T1. Vertices that touch faulty edges. Okay, so F and S are the same, but now I define T1 instead of T delta 0 over 2. I look at T1, but new faulty edges. Not necessarily in F, as I run a correction step and I change things. And I want to claim that, again, this happens. Okay, this is a little confusing. It took me some time to digest. Once again,
So in the analysis, the faulty edges, we're talking about local faulty, not faulty in terms of from C. It's not the non-trivial edges of E.
It is the faulty edges according to E. Okay, because after I ran a correcting step, each vertex sees a word in the code C0, right? That's the meaning of running.
But that's what I'm asking. Are we defining the faulty stuff by the little deltas, by the little C0, or by
by E? We had the W equals C plus E, and E evolves over time. We always, okay, so this is the code. We get C, and we get somewhere near, and the error evolves until it collapses to C. And we track the errors, these errors, the E as it evolves. Okay, and so I want to claim the same thing, and the only thing I need to say is that T1 is a subset of T delta naught over 2, but this one is from the previous argument. I mean, in other words, each vertex in T1 must touch at least delta 0 over 2 elements in F. Okay, this is really confusing because F is from the previous step. Okay, but in order for a vertex to be in T1, it means that I corrected it to the wrong node. Can you see it? For a vertex to be in T1, when I'm correcting step on I, now vertex has faulty edge. So it sees the wrong word from C0. Okay, I see I'm losing people and we're running out of time. So make sure you understand that each vertex in T1 has to touch at least delta 0 over 2 edges in F. And then this claim ends. The lemma ends the proof when this is T1 and S1. And this is basically the end of the proof of the decoding algorithm, because we will correct the left side and then the right side and then the left side again. And S and T will shrink by a multiplicative factor of 3 over 4 in each iteration. And so after log n order of log n iteration, the algorithm terminates because S and T are 0. And we have no vertices that touch faulty edges, which means there are no faulty edges. Okay, I think it's better to end the class now because we're over time. But I'll upload my notes and you can see everything there. Thank you, and sorry for the delay.